There is a spacecraft moving through the darkness right now. It has been moving for 47 years without stopping, without slowing, without any destination it was ever designed to reach. It carries no passengers. It has no windows. Its nuclear power source is fading so gradually that engineers measure its decline in fractions of a watt per year. Its antenna, a dish 3.7 meters wide, points back toward a pale blue dot so distant that the radio signals it sends home, traveling at the speed of light, take more than 22 hours to arrive. By the time you finish listening to what I'm about to tell you, another signal will have crossed that gulf. Another data packet from the edge of everything we have ever touched will have reached the hands of the people who still listen. That spacecraft is Voyager 1. And what it has been finding in the last several years has quietly dismantled some of the most confident predictions in the history of planetary science. Not partially dismantled, not challenged in ways that require minor adjustments, dismantled in the way that forces scientists to sit down, go back to first principles, and admit that something fundamental about the structure of our solar system, about the boundary between what belongs to our sun and what belongs to the galaxy, is not what anyone thought it was. The data coming back from Voyager 1 has revealed a region of space that behaves according to rules nobody wrote, a transition zone that does not match a single major theoretical model, and electromagnetic phenomena that are, as of this recording, without a confirmed scientific explanation. This is not a story about a spacecraft malfunctioning. Voyager 1 is working. That is precisely what makes this so extraordinary. What you're going to understand by the end of what I am about to tell you is this. The boundary of our solar system, a structure called the heliosphere, was supposed to be one of the best understood large-scale features of our cosmic neighborhood. Decades of theoretical modeling, backed by laboratory physics and corroborated by earlier spacecraft, had produced a picture that scientists were genuinely confident in. Voyager 1 was not sent to discover surprises at the edge. It was sent, in part, to confirm what we already thought we knew. Instead, it has spent the better part of a decade sending back measurements that contradict the model at nearly every scale. From the microscopic behavior of individual charged particles to the large-scale geometry of the boundary itself. And the deeper the spacecraft travels into the region beyond, the stranger the data becomes. We will get to all of it. But to understand why these findings are so disorienting, you need to understand what the heliosphere actually is, why scientists thought they understood it, and what crossing its boundary was supposed to look like. Because the contrast between the prediction and the reality is where the real story lives. If you find this kind of deep, careful exploration of the universe valuable, consider subscribing if you have not already. It genuinely helps this channel reach more people who want to think about these things seriously. Now, let us go back to where this story begins. The Sun is not a passive object sitting at the center of the solar system. It is constantly producing something. Every second of every day, the Sun emits a stream of charged particles, mostly electrons and protons, that flows outward in all directions at speeds ranging from 300 to 800 kilometers per second. This is the solar wind. It is not metaphorical. It is a physical flow of matter leaving the Sun continuously, carrying with it a magnetic field that is rooted in the Sun itself and spirals outward as the Sun rotates, like water spinning off a garden sprinkler, stretching and winding across billions of kilometers of space. This solar wind does not flow forever without consequence. As it moves outward, it eventually encounters the gas and dust and charged particles that fill the space between star systems. A medium called the interstellar medium. The interstellar medium is not empty. It has its own pressure, its own magnetic field, its own particle populations. At some point, the outward pressure of the solar wind becomes equal to the inward pressure of the interstellar medium. At that point, the solar wind slows, and in slowing, it creates a structure. The entire bubble of space enclosed within this balance of pressures is what scientists call the heliosphere. Picture it as a vast invisible sphere, or more accurately, an elongated, teardrop-shaped region surrounding the entire solar system. The Sun sits near one end. The planets, all of them, orbit well within its interior. Even Neptune, at an average distance of 30 astronomical units from the Sun, where 1 astronomical unit is the distance from the Earth to the Sun, or sits deep inside the heliosphere with hundreds of astronomical units of protective bubble still extending beyond it. The heliosphere is not merely a conceptual boundary, it is a physical shield. The charged particles that fill the galaxy, cosmic rays produced by distant supernovae and other violent processes across billions of light years, are partially deflected and attenuated by the heliosphere. The magnetic structure of the solar wind disrupts their paths, reducing the flux of high-energy particles reaching the inner solar system by a significant margin. Without the heliosphere, Earth and the other planets would be exposed to a substantially higher bombardment of galactic cosmic radiation. The heliosphere is, in a very real sense, one of the conditions that makes the inner solar system a more manageable environment. By the 1980s, scientists had a working theoretical model for what the outer heliosphere looked like and how its boundary regions were structured. This model, built on decades of plasma physics and magnetohydrodynamics, predicted a layered structure. Starting from the inside and moving outward, the model described the supersonic solar wind flowing at full speed through the inner heliosphere, then a transition region called the termination shock, where the solar wind slows dramatically as it begins to encounter resistance, then a thick, turbulent zone called the heliosheath, where the slowed solar wind piles up and becomes compressed and chaotic. And finally, the outer boundary itself, the heliopause, where the solar wind material ends and true interstellar space begins. The model was elegant, it was grounded in well-tested physics. It was supported by computer simulations of increasing sophistication. And it made specific, testable predictions about what any spacecraft crossing these boundaries would measure, how particle densities would change, how magnetic field directions would shift, how the energies of detected particles would transform from one regime to the next. Voyager 1 was going to be the test. The spacecraft was launched on September 5, 1977. Its primary mission was to visit Jupiter and Saturn, which it did with breathtaking success. The gravity of Saturn then bent the spacecraft's trajectory northward and out of the ecliptic plane, the flat disk in which most of the planets orbit. That trajectory meant Voyager 1 was not headed toward any other planet. It was headed out, away from the Sun, away from the solar system, along a path angled roughly 35 degrees above the ecliptic and aimed toward the constellation Ophiuchus. By the 1990s, after its planetary encounters were long behind it, Voyager 1 had become something different from what it was designed to be. It had become an interstellar probe by default. Scientists who had designed its instruments for close-range planetary study realized that some of those instruments could still detect the low-energy, charged particles and magnetic fields of deep space, the spacecraft was still functioning. It was still transmitting, and it was headed toward the boundary. The question was, what would crossing that boundary actually look like in the data? Based on the theoretical model, scientists expected a specific sequence of events as Voyager 1 moved through the outer heliosphere. First, the spacecraft would detect the termination shock as a sharp region where solar wind proton velocities dropped dramatically from supersonic to subsonic. Second, it would enter the heliosheath and spend years traveling through a thick layer of hot, compressed, turbulent plasma. Third, it would detect the heliopause as an equally sharp boundary where solar wind particles essentially disappeared and interstellar particles took their place. The magnetic field would shift direction to align with the broader interstellar field rather than the solar wind's spiral pattern. The cosmic ray flux, the particles coming from outside the solar system, would jump sharply as the spacecraft crossed into unshielded interstellar space. Clean, sequential, detectable. The crossing was supposed to look like a series of threshold events. In 2004, Voyager 1 detected the termination shock. The solar wind velocity dropped. The model had predicted this at somewhere between 80 and 100 astronomical units from the Sun. The actual crossing happened at approximately 94 astronomical units. That was close enough to feel like a confirmation. Scientists noted the slight discrepancy, attributed it to the dynamic nature of the solar wind varying with solar activity, and moved on. The model was holding. Then things got strange. The heliosheath was supposed to be a bounded, measurable region. The theoretical models suggested it would be somewhere between 30 and 50 astronomical units thick, perhaps as much as 80 astronomical units under certain assumptions about the pressure of the interstellar medium. Voyager 1 entered the heliosheath in 2004 and spent the next 8 years traveling through it. 8 years of data from a region that was supposed to be reasonably well understood. And during that entire period, the behavior of the solar wind, the magnetic field directions, the particle populations, all of it was more complex, more variable, and more disorganized than any model had predicted. But the real surprise was waiting at the other end. In August of 2012, based on a cluster of simultaneous measurements, scientists at the Jet Propulsion Laboratory and collaborating institutions determined that Voyager 1 had crossed the heliopause. It had left the heliosphere. It had entered interstellar space. This was a historic moment by any measure. A human-made object had, each for the first time in the history of civilization, travelled beyond the influence of its home star and entered the space between the stars. No one alive had seen this happen before. No one would live to see it happen again from another spacecraft for many decades, at minimum. The instruments confirmed the crossing with remarkable clarity. The flux of low-energy solar wind particles dropped to near zero. The flux of galactic cosmic rays jumped sharply. The magnetic field shifted. All of these changes happened within a period of roughly 2 months, which on the scale of interstellar distances is essentially instantaneous. The heliopause at this point looked just like the model predicted, a sharp, relatively clean boundary. For a brief moment it seemed like the story was one of triumph. The model had worked. The physics had been right. Voyager 1 had confirmed the basic architecture of the heliosphere's outer boundary. That moment of triumph did not last long. Because once scientists began analyzing the data from beyond the heliopause in detail, something became clear that no one had anticipated. The interstellar space that Voyager 1 had entered was not the interstellar space that the theoretical models described, not in its density, not in its magnetic field orientation, not in the behavior of the particles detected, and not, most importantly, in what the region was doing to the spacecraft's own measurements in ways that have still not been explained. The data from interstellar space, the first direct in situ measurements of the actual material between the stars, showed properties that differed from predictions in multiple independent ways simultaneously. And this was not a single anomaly in one instrument that could be attributed to sensor drift or calibration error. It was a coherent pattern of discrepancy running across different instrument types, measuring different physical quantities. The kind of discrepancy that forces a community to revisit its assumptions rather than its instruments. And then, about 4 years after the heliopause crossing, something happened in the data that scientists are still trying to explain. Voyager 1 detected a series of electron-plasma oscillations, vibrations in the plasma of the local interstellar medium that were far more intense and far more organized than anyone had predicted. These oscillations allowed scientists to calculate the electron density of the surrounding interstellar medium for the first time using direct measurement rather than inference. And that density measurement was 3 to 4 times higher than the best theoretical estimates had predicted. Not slightly higher, not at the edge of the error bars, 3 to 4 times higher. Hold that number in your mind, we will come back to it. But that was not the most disorienting finding. Because alongside the plasma density anomaly, the data revealed something about the structure of the boundary zone itself, about the geometry and the physics of the region between the edge of the heliosphere and the deeper interstellar medium that has produced what scientists have described in published papers using language that is, by academic standards, remarkably candid. Language about incompleteness, about fundamental gaps in the model, about the realization that the heliosphere's interaction with the interstellar medium may be governed by physical processes that have not yet been incorporated into any theoretical framework. To understand why this matters so deeply, we need to step back from Voyager 1 for a moment and understand what the interstellar medium actually is, because the surprise at the boundary only makes sense when you understand what was supposed to be on the other side of it. The interstellar medium is the material that fills the space between star systems in our galaxy. It is not nothing. It is not even close to nothing by the standards of everyday vacuum, though by most human standards it would qualify as an exceptionally good vacuum. It consists of gas, dust, magnetic fields, and charged particles spread across the vast distances between stars. Its composition is dominated by hydrogen and helium, with trace amounts of heavier elements in proportions that reflect the chemical evolution of the galaxy over billions of years. This medium is not uniform. It is structured, layered, turbulent on scales ranging from the subatomic to the interstellar. The region of the interstellar medium through which our solar system is currently traveling has a name. Scientists call it the local interstellar cloud, sometimes called the local fluff, a designation that understates what it actually is. This cloud is a region of partially ionized gas, roughly 30 light-years across. And our solar system has been moving through it for somewhere between 45,000 and 150,000 years, and will continue to do so for roughly 10,000 to 20,000 more years before we potentially exit into a different region of the local interstellar medium. The properties of the local interstellar cloud matter enormously to the shape and behavior of the heliosphere. The pressure of this cloud's gas and magnetic field is what the solar wind is pushing against. The density and ionization state of the cloud determines how much neutral gas can penetrate the heliosphere. The temperature and turbulence of the cloud affects the structure of the boundary layers. Every aspect of the heliosphere's outer architecture is a negotiation between the Sun and this cloud. And Voyager 1, in crossing the heliopause, did not just cross a boundary, it crossed into a medium that we had never directly sampled before, and whose properties, based on everything we thought we knew about the local interstellar cloud, should have been broadly predictable. They were not. The plasma density was wrong by a factor of 3 to 4. The magnetic field direction was closer to predictions than some scientists expected, but had features that still required explanation. And there was a phenomenon at the boundary itself, a thin zone of material that exhibited characteristics partway between the heliosheath and the interstellar medium proper, something that the standard model had either not predicted or had predicted in the wrong way. Scientists called this the heliospheric boundary layer. And its existence raised a question that cuts to the heart of what Voyager has revealed. If the heliopause is a boundary, where exactly is it? Because what Voyager 1 found was not a clean wall. What it found was something fuzzier and stranger than that. In the months and years after the initial heliopause crossing, Voyager 1 continued to detect brief excursions back into regions of space that had the characteristics of heliospheric material rather than interstellar material. The magnetic field would briefly shift back toward the configuration typical of the heliosheath. Solar wind particles that had supposedly been left behind would appear again for short periods, and then, just as quickly, the measurements would return to interstellar values. What was happening? Was the heliopause moving? Was it rippling like a flag in a slow wind? And so that Voyager 1 was periodically passing back through its folds? Was there a mixing layer of indeterminate thickness where neither solar wind material nor interstellar material dominated, but both coexisted in some complex, turbulent combination? And if so, how thick was this mixing layer, and what were the physics of the mixing process? The standard models had assumed the heliopause was a fairly sharp interface. Observations from earlier spacecraft, particularly measurements of energetic neutral atoms that had travelled from the boundary region inward where they could be detected, suggested some structure beyond simple sharpness, but nothing in the pre-crossing predictions fully accounted for what Voyager 1 found in the first years beyond it. As of the most recent data transmissions from Voyager 1, the spacecraft is approximately 160 astronomical units from the Sun. To put that number in perspective, consider that 1 astronomical unit is roughly 149 million kilometers. 160 astronomical units is therefore approximately 23.8 billion kilometers. The light travel time from the spacecraft to Earth is now roughly 22 hours and 20 minutes one way. When the engineers at the Jet Propulsion Laboratory send a command to the spacecraft, they wait 44 hours and 40 minutes for the round-trip signal to confirm the command was received and executed. At this distance, Voyager 1 is sampling the interstellar medium at a location roughly 35 degrees above the ecliptic plane, angled toward the nose of the heliosphere, the direction from which the Sun is moving relative to the local interstellar medium. This is actually one of the most scientifically interesting directions to probe, because the nose region is where the solar wind and the interstellar medium are in most direct confrontation, where the pressures are most evenly balanced, and where the structure of the boundary is most dynamically active. And from this vantage point, Voyager 1 is continuing to return data that does not fit. The electron density measurements, which should in principle converge toward a stable interstellar background value as the spacecraft moves deeper into the interstellar medium, have instead shown persistent variation. The density is not uniform, it fluctuates, it shows structure on scales of a few astronomical units. And the nature of those fluctuations does not match the turbulent spectrum predicted by standard models of interstellar medium physics. This matters because turbulence in the interstellar medium is not a secondary detail. It is fundamental to how energy propagates through the medium, how cosmic rays scatter and diffuse, how magnetic field lines are structured across large scales, and ultimately, how the interstellar medium as a whole evolves over time. If the turbulence properties measured directly by Voyager 1 in the very local interstellar medium differ from what models predict, then those models, which are used to understand not just our solar neighborhood, but the dynamics of interstellar media in other parts of the galaxy, need revision. And here is something worth sitting with for a moment. If Voyager 1 did not travel to the interstellar medium on purpose, in the way that, say, a Mars probe is designed to study Mars, it got there because the laws of physics carried it there, because a sequence of planetary gravity assists designed to study Jupiter and Saturn happened to place it on a trajectory that, over 47 years of unpowered flight, eventually reached the boundary of the solar system. The fact that it still has working instruments capable of making these measurements is the result of engineering decisions made in the early 1970s by people who are now in their 80s. People who hoped the spacecraft might last long enough to see the termination shock, but never dared to be certain it would still be transmitting from beyond the heliopause. There is something profound about that, not just technologically, existentially. The most far-reaching and disorienting measurements ever taken from beyond our solar system are being taken by an instrument built with the technology of the Apollo era, running software that occupies a fraction of the memory of a digital watch, kept alive by a nuclear battery that has been slowly releasing heat for nearly half a century. And it is still finding things we do not understand. But the plasma density anomaly, as unsettling as it is not the most mysterious thing Voyager 1 has found. There is something else in the data, something that was noticed and quietly flagged in scientific publications starting in around 2017, and that has grown more difficult to explain, not easier, as more data has accumulated. It has to do with the magnetic field, specifically with the direction of the magnetic field in the local interstellar medium, and with what that direction tells us about whether our entire theoretical picture of the Sun's interaction with the galaxy is not just incomplete, but oriented in the wrong direction entirely. We will get to that. But first, we need to understand exactly how Voyager 1 detects a magnetic field across 23 billion kilometers of space, and why the direction of that field, a parameter that seems almost too abstract to matter, turns out to be one of the most consequential variables in understanding the shape and behavior of the entire heliosphere. The magnetometer aboard Voyager 1 is not a complicated instrument by modern standards. It consists of two sets of sensors mounted on a long boom extending from the spacecraft body, a design intended to place the sensors as far as possible from the magnetic interference generated by the spacecraft's own electronics and power systems. The principle behind the measurement is straightforward. A magnetic field exerts a force on a current-carrying conductor. By measuring that force with precision, you can determine the strength and direction of the ambient field at the spacecraft's location. The instrument was calibrated before launch, cross-checked against known references during the mission, and its readings have been continuously compared against independent measurements from other instruments to verify their consistency. At 160 astronomical units from the Sun, the magnetic field Voyager 1 is measuring is extraordinarily weak. We are talking about field strengths measured in units of microgauss, where 1 microgauss is 1/1,000,000th of a gauss, and 1 gauss is already a relatively modest field strength by terrestrial standards. The Earth's own magnetic field at the surface runs between about 0.25 and 0.65 gauss. The interstellar magnetic field that Voyager 1 is measuring is roughly 5 orders of magnitude weaker than that. To say the measurements are at the edge of the instrument's sensitivity is not an overstatement. And the fact that they can be made reliably at all is a testament to the care with which the magnetometer was designed and the sophistication of the data processing applied to the raw signal on the ground. But the measurements are reliable. And what they show has forced a fundamental reconsideration of something that seemed, before Voyager 1's crossing, to be relatively well constrained. The direction of the interstellar magnetic field matters enormously because it determines the shape of the heliosphere. The heliosphere is not a perfect sphere. The solar wind flows outward with roughly equal strength in all directions from the Sun, but the interstellar medium does not push back equally from all sides. The interstellar medium has a bulk flow, a direction from which it appears to be approaching the solar system as the Sun moves through the galaxy. And it has a magnetic field with a preferred orientation. These two properties, the direction of the interstellar flow and the direction of the interstellar magnetic field, together with the pressure of the solar wind, determine the three-dimensional shape of the heliosphere. Before Voyager 1 crossed the heliopause, the best estimates for the direction of the interstellar magnetic field came from indirect measurements. One of the most important of these came from a spacecraft called the Interstellar Boundary Explorer, launched in 2008, which did not travel to the boundary, but instead detected energetic neutral atoms, fast-moving neutral particles created at the boundary region, and mapped their arrival directions to build a picture of the heliosphere's global structure. Based on these measurements and on theoretical modeling, scientists had developed a consensus picture of the interstellar field direction. It was expected to run at a modest angle to the direction of interstellar flow, roughly consistent with measurements from other nearby stars and with models of the local galactic magnetic field. That consensus picture had a specific implication. If the interstellar magnetic field runs at a modest angle to the interstellar flow direction, the heliosphere should be roughly symmetric around the direction of interstellar flow. It should look, if viewed from above, something like a blunt-nosed object with a long tail, the tail extending in the direction away from the oncoming interstellar wind, the nose relatively round and compressed. The two sides of the heliosphere, left and right, relative to the interstellar flow direction, should be roughly mirror images of each other. Not perfect mirrors, because the solar wind has its own variability, and the interstellar medium has local structure, but broadly symmetric. Voyager 1 is probing the nose region of the heliosphere, travelling outward at an angle roughly in the direction from which the interstellar wind appears to approach. Voyager 2, its sister spacecraft, launched 16 days earlier on August 20th, 1977, on a different trajectory that took it past Jupiter, Saturn, Uranus, and Neptune before sending it outward, is probing a region roughly in the opposite hemisphere of the heliosphere, about 36 degrees below the ecliptic plane, that angled more toward the flank and tail region. Voyager 2 crossed the heliopause in November of 2018, 6 years after Voyager 1, at a distance of approximately 119 astronomical units from the Sun. That is nearly 41 astronomical units closer than where Voyager 1 crossed. Let that sink in for a moment. The same boundary, the heliopause, crossed at vastly different distances on two different sides of the heliosphere. If the heliosphere were symmetric, the crossing distances should be roughly comparable. The fact that they differed by about 41 astronomical units is itself a major finding, one that tells us the heliosphere is significantly asymmetric. The nose, where Voyager 1 crossed, is pushed out much further by the solar wind than the region where Voyager 2 crossed. But when scientists compared the magnetic field measurements from both spacecraft in the interstellar medium, something even more striking emerged. The direction of the magnetic field that Voyager 1 measured beyond the heliopause and the direction that Voyager 2 measured beyond the heliopause were not the same. They differed by an amount that exceeded the uncertainty in both measurements, and neither direction matched the pre-crossing consensus prediction particularly well. Now, a local interstellar magnetic field that varies in direction over the scale of the distance between the two Voyager crossing points is not, by itself, impossible. The interstellar medium has turbulence and structure. Local variations in field direction are expected, but the magnitude of the discrepancy and the fact that it was correlated with specific features in the particle and plasma data at each crossing point suggested that something more systematic was at work. Some scientists proposed that the heliosphere was deflecting and draping the interstellar magnetic field around itself in a more complex way than the models assumed. In this picture, the field lines of the interstellar medium do not simply terminate at the heliopause. They bend around the heliosphere, wrapping around the boundary surface in a pattern that depends on the heliosphere's shape, its orientation relative to the interstellar flow, and the compressibility of the field. If this draping is significant, then the field direction measured just outside the heliopause, where both Voyagers crossed, might not represent the unperturbed interstellar field at all. It might represent a locally modified field bent by the very presence of the heliosphere. If that is the case, then the direct measurements from both Voyager spacecraft, rather than giving us the true direction of the interstellar field, are giving us the direction of a field that has already been wrapped and warped by the heliosphere's influence. To get the true background field direction, you would need to go much farther from the heliosphere, far enough to escape its gravitational and electromagnetic shadow and sample the interstellar medium in a region that has not been disturbed by the Sun's influence. Neither Voyager spacecraft is there yet, and the implications of not knowing the true background field direction are not trivial, because the shape of the heliosphere, and therefore the level of cosmic ray shielding that the inner solar system receives, depends sensitively on the angle between the interstellar flow direction and the interstellar field direction. Change that angle even by 20 or 30 degrees, and the heliosphere's shape changes substantially. The asymmetry between the two sides changes, the length of the tail changes, and the efficiency of cosmic ray deflection changes. We are, in other words, not entirely sure of the shape of the structure that partially shields life on Earth from the full flux of galactic cosmic radiation. That is the depth of the uncertainty that Voyager 1's measurements have introduced. But there is another anomaly in the data, one that emerged more slowly and has been harder to interpret, and which touches on something even more fundamental. It has to do with what happens to particles when they cross the heliopause, and specifically with a category of particles that were not supposed to behave the way they are behaving. Galactic cosmic rays are charged particles, mostly protons, alpha particles and electrons, accelerated to enormous energies by supernova remnants, pulsar wind nebulae, and other violent processes scattered across the galaxy. They travel through the interstellar medium in all directions, filling the galaxy with a diffuse, isotropic sea of high-energy radiation. When they reach the heliosphere, they interact with the solar magnetic field embedded in the solar wind. The turbulent, tangled field of the heliosphere scatters their paths, reducing their penetration into the inner solar system. This is the shielding effect of the heliosphere, and it is real and measurable. The theoretical prediction was that when Voyager 1 crossed the heliopause, the galactic cosmic ray flux would jump sharply, because the shielding would drop away and then would stabilize at a roughly constant background level representing the undisturbed interstellar cosmic ray population. The initial crossing in 2012 did show a sharp jump in cosmic ray flux, just as predicted. So far, so good. But in the years after the crossing, the cosmic ray flux has not stayed constant. It has continued to vary. It has shown structures and modulations that correlate, in some cases, with events happening back at the Sun. Events like large solar eruptions that send pressure waves propagating outward through the solar wind. Those pressure waves, it turns out, can propagate through the heliopause and cause detectable disturbances in the interstellar medium just outside the boundary. The heliosphere is not a perfect sealed container. It leaks its internal dynamics outward, and the interstellar medium just outside it carries the imprint of those dynamics for farther than anyone had anticipated. This is scientifically important for a reason that goes beyond Voyager's own mission. Every star with a stellar wind, which is most stars, creates its own version of a heliosphere, called an astrosphere. The interaction between that astrosphere and the surrounding interstellar medium is a key process in the chemistry and physics of the interstellar medium itself, in how molecular clouds form, in how star formation proceeds, in how energy is transferred across galactic scales. If the Sun's heliosphere is leaking its dynamics into the surrounding medium in ways we did not anticipate, then the same is likely true of other stellar winds around other stars and the models of interstellar medium physics that underlie our understanding of galactic evolution may need revision. Now consider that we have exactly one data point for a spacecraft in the local interstellar medium. 1. Voyager 1. And a second data point with different characteristics from Voyager 2 crossing at a different location. 2 data points to constrain the properties of a medium that extends across the entire galaxy. The statistical confidence we can place on any specific measurement from those 2 points is limited by the fact that we do not know how representative they are of the broader interstellar medium. They might be in an unusual local structure. They might be sampling the interstellar medium at a time when solar activity is anomalously high or low. They might be measuring something specific to the nose and flank regions of the heliosphere rather than properties that generalize to all heliospheric crossing points. This is not a criticism of the mission or the measurements. It is simply a recognition of the extraordinary difficulty of doing science with two data points at the edge of the solar system. Every anomaly detected by Voyager 1 could be a fundamental property of the interstellar medium, or it could be a local feature specific to this particular place and time. Disentangling those two possibilities requires more data from different crossing points at different times. And the only way to get that data is to send more spacecraft. Spacecraft that do not yet exist. Spacecraft whose design, funding, and launch are decades away at best. In the meantime, we have Voyager 1. And what Voyager 1 is telling us from its single vantage point is strange enough to demand explanation. Here is one of the strangest things, and this is the finding that, when you spend time with it, starts to feel less like a calibration anomaly and more like a window into something genuinely unknown. In 2021, a team of scientists analyzing Voyager 1 data published a paper describing a persistent, low-level hum in the plasma of the local interstellar medium. Not a hum in the acoustic sense. The interstellar medium cannot carry sound waves in the way air does, but it can carry electromagnetic plasma oscillations. See waves in the density of the electron population that propagate at characteristic frequencies determined by the electron density itself. These are called plasma waves. And when Voyager 1's plasma wave instrument picks them up, they are converted into a signal that, when played at audible frequencies, sounds like a faint, steady tone. This hum was there in the data between the large plasma oscillation events triggered by solar eruptions that I mentioned earlier. In the quieter periods when no major disturbance from the sun was propagating through the region, the plasma was still oscillating, weakly, persistently, at a frequency corresponding to an electron density of roughly 0.13 electrons per cubic centimetre. That number is significant for two reasons. First, it corresponds to the independently derived estimates of the electron density in the local interstellar cloud, confirming that the spacecraft is genuinely sampling the ambient interstellar medium rather than some transitional or boundary-influenced region. Second, the persistence and uniformity of the hum suggests that the local interstellar medium has a measurable baseline level of plasma wave activity that is not driven by external events. Something is sustaining these oscillations continuously. Something is putting energy into the plasma at a steady rate, maintaining a low but non-zero level of electromagnetic activity in what should be, by some theoretical descriptions, a relatively quiescent medium. What is driving this hum? The honest answer is that it is not entirely clear. One hypothesis involves the interstellar magnetic field itself, whose turbulent fluctuations can drive plasma oscillations through magnetohydrodynamic processes. Another involves cosmic ray electrons, which can excite plasma waves through a process called the beam instability as they stream through the medium. A third involves the direct interaction between the heliospheric boundary and the surrounding medium, a kind of electromagnetic wake left by the passage of the heliosphere through the interstellar gas. None of these hypotheses is fully satisfactory. All of them predict some level of background plasma wave activity, but none of them in their current forms predict the specific amplitude and frequency stability that Voyager 1 is measuring. The hum is more consistent and its frequency more steady than any of the proposed mechanisms naturally produce. And there is something that makes this particular mystery more acute than it might seem from the description. Plasma wave frequencies in the interstellar medium are not just a curiosity. They are one of the primary tools scientists use to measure electron density, to track the propagation of disturbances, and to understand how energy moves through the medium on large scales. If the background level of plasma wave activity is higher and steadier than models predict, then some of the measurements derived from those waves, including the density estimates, the propagation speed calculations, the energy budget analyses, may be systematically off in ways that have not yet been fully characterized. In other words, the hum might not just be unexplained. It might be contaminating other measurements in subtle ways that compound the uncertainty in everything else Voyager 1 is telling us. This is the layered nature of the problem. It is not one anomaly. It is a set of interrelated anomalies, each of which could in principle have an innocent explanation, but which together form a pattern that points toward fundamental incompleteness in the theoretical framework. The plasma density is wrong by a factor of 3 to 4. The magnetic field direction does not match predictions and varies unexpectedly between the two Voyager crossing points. The cosmic ray modulation extends farther beyond the heliopause than models allow. And now there is a steady electromagnetic hum in the interstellar plasma that no one has adequately explained. Each of these is a problem. Together, they are a message. Or the message is not that our physics is wrong in some catastrophic way. The basic equations of plasma physics, magnetohydrodynamics, and particle transport that underlie the heliospheric models are well tested and broadly valid. The problem is not with the physics. The problem is with the geometry, the boundary conditions, and the specific local properties of the environment our solar system is traveling through. We built detailed models of the heliosphere's outer boundary using assumptions about the surrounding interstellar medium that were derived indirectly from remote observations, from theoretical estimates, from analogies with other stellar systems. And when Voyager 1 went there and measured the medium directly, the medium was not what we assumed. The local interstellar cloud, it turns out, is stranger than we thought. But here is the thing about the local interstellar cloud that makes this even more consequential and that pushes the story from the merely scientific into something more profound. The cloud we are traveling through is not the typical state of the interstellar medium. It sits within a larger structure called the local bubble, a vast region of extremely low density, hot plasma roughly 1,000 light-years across, carved out of the interstellar medium by a series of supernova explosions that occurred somewhere between 10 million and 20 million years ago. The local bubble is, in the context of the galaxy, a peculiar environment. Most of the galaxy's interstellar medium is denser, cooler, and more magnetically complex than the interior of the local bubble. Our solar system has been inside the local bubble for most of its recent geological history. We have been drifting through this enormous, hot, tenuous cavity, occasionally passing through small, denser cloudlets, like the local interstellar cloud, but fundamentally insulated from the denser and more active interstellar medium that characterizes most of the galaxy. The properties that Voyager 1 is measuring in the local interstellar medium are not the properties of the interstellar medium in general. They are the properties of a specific, unusual pocket within an unusual bubble within one arm of one galaxy. And yet those properties are the ones that determine the shape and strength of the heliosphere that partially shields the inner solar system from galactic cosmic radiation. If the solar system were in a denser region of the interstellar medium, the heliosphere would be compressed. If the solar system were in a region with a stronger interstellar magnetic field, the heliosphere's shape would be different. If the solar system were in a more turbulent region, the heliopause would be more dynamic and less stable. The fact that we exist in a cosmic neighborhood that supports a robust heliosphere may not be a coincidence. It may be a consequence of the specific trajectory the solar system has followed through the galaxy over the last several billion years. A trajectory that has kept us, for the most part, away from the densest and most hostile regions of the interstellar medium. The heliosphere is not just a scientific object, it is one of the conditions of our existence. And Voyager 1. In the act of crossing it and measuring what lies beyond, has revealed that we understood that condition less completely than we thought. What makes the situation even more intriguing is that the local interstellar cloud itself is a transitional environment. The solar system is near the edge of it. Within the next 10,000 to 20,000 years, we will potentially exit the local interstellar cloud and enter a different region of the local interstellar medium, possibly a region with different density, different temperature, different magnetic field properties. When that happens, the heliosphere will respond. It will change shape. The termination shock will move. The heliopause distance will shift. The level of cosmic ray shielding reaching the inner solar system will change. By how much? We do not know precisely, because we do not know precisely what lies on the other side of the local interstellar cloud's edge. But the fact that Voyager 1's measurements have revealed that the current properties of the local interstellar medium differ from theoretical predictions suggests that the models used to predict what the next interstellar environment will look like are also subject to significant uncertainty. We are moving through a galaxy we do not fully understand, in a bubble carved by ancient violence, wrapped in a magnetic shield whose true shape we cannot determine, surrounded by a plasma whose fundamental properties continue to surprise us. And we know this because of one spacecraft. One spacecraft launched 47 years ago, running on 40 watts of power, transmitting data at the rate of 160 bits per second from a distance so vast that its signals take almost a full day to arrive. The technology is not the story, but the technology makes the story possible. And without understanding what Voyager 1 is, what it is doing, and what it is up against in the act of simply continuing to function at this distance, the full weight of what it is telling us cannot be properly felt. Voyager 1's power comes from 3 radioisotope thermoelectric generators. These devices convert the heat produced by the natural radioactive decay of plutonium-238 into electricity through a process that involves no moving parts, no combustion, no solar panels, nothing that can clog or freeze or run out of fuel in the conventional sense. The decay process cannot be stopped. It proceeds according to the laws of nuclear physics on a timeline indifferent to human need. Plutonium-238 has a half-life of approximately 87.7 years, meaning that every 87.7 years, the amount of plutonium in the generator decreases by half, and therefore the heat output decreases by half, and therefore the electrical power available to the spacecraft decreases by half. At launch in 1977, the 3 generators together produced approximately 470 watts of electricity. Today, after nearly 48 years of decay, they produce roughly 40 watts. The spacecraft's designers knew this day was coming. They planned for it. Over the decades, as power has declined, SUA engineers have systematically shut down instruments and heaters to concentrate the remaining power on the most scientifically valuable systems. Today, Voyager 1 operates only a handful of instruments: the plasma wave subsystem, the magnetometer, the low-energy charged particle detector, the cosmic ray subsystem, and the spacecraft's basic housekeeping systems, the attitude control, the telecommunications hardware, the command computer. The instruments that have been shut down will never be turned on again. The power is not there. And the power available to the remaining instruments is declining by roughly 4 watts per year. At some point, probably in the late 2020s or very early 2030s, the power will drop below the threshold needed to operate any scientific instrument. After that, next Voyager 1 will still be out there, still moving, still transmitting perhaps, but with nothing to say. A ghost ship in the interstellar medium, carrying its golden record of Earth sounds and its corroding, cooling generators into a silence that will last longer than the sun itself. Before that happens, there is more science to be done. And some of the most important science involves a question that the plasma density anomaly, the magnetic field discrepancy, and the electromagnetic hum have collectively raised. What is the three-dimensional structure of the heliosphere's boundary, and does that structure have anything to do with a long-standing mystery about the shape of the heliosphere itself? That mystery has a name. Scientists call it the heliotail problem. And understanding it requires us to think about the heliosphere not as a static object, but as a dynamic structure in motion, travelling through a medium it is constantly interacting with, leaving a wake behind it, just as a boat leaves a wake in water. The heliosphere has a nose, the compressed leading edge in the direction of the sun's motion relative to the interstellar medium, and a tail called the heliotail, extending in the opposite direction. The nose is where Voyager 1 is probing. The tail, in principle, extends for hundreds or even thousands of astronomical units behind the sun. Its length, shape, and interior structure have been matters of significant debate. For decades, the dominant theoretical picture of the heliotail was relatively simple. It was expected to be a long, roughly cylindrical structure containing a mix of slower solar wind and some recaptured interstellar neutral atoms, tapering gradually into the interstellar medium over a distance of perhaps a few hundred astronomical units. Simple, bounded, predictable. Then, in 2013, the Interstellar Boundary Explorer spacecraft produced a map of energetic neutral atom emission from the boundary region, and the map showed something that no one expected. The heliotail was not cylindrical, it was not simple, and it was not bounded in the way anyone had predicted. The map showed that the heliotail region was structured into at least 2 distinct lobes, extending in different directions, with a clover-like cross-section rather than the smooth cylindrical shape the models had assumed. One lobe extended roughly northward, angled above the ecliptic plane. Another extended southward. The 2 lobes were separated by a region of higher energy particles forming a kind of belt around the tail's equatorial cross-section. The entire structure was twisted relative to the expected axis of the sun's motion through the interstellar medium. The twist was the clue. Because a twisted heliotail does not arise from a symmetric interaction between the solar wind and the interstellar medium. It arises when the interstellar magnetic field is not aligned with the interstellar flow direction. When the field runs at an angle to the flow, it applies an asymmetric pressure to the sides of the heliosphere, compressing one flank more than the other and twisting the tail as a consequence. The degree of twist observed in the energetic neutral atom map implied a specific relationship between the interstellar flow direction and the interstellar field direction. But here is the problem. The twist implied by the energetic neutral atom map, was not consistent with the interstellar magnetic field direction measured directly by Voyager 1 beyond the heliopause. Two independent measurements using two completely different techniques, sampling different aspects of the same physical system, were pointing to different answers about the orientation of the interstellar magnetic field. This is not a small discrepancy between different measurement approaches that can be explained by calibration differences or systematic errors. This is a fundamental tension between two independent lines of evidence, and it means that either the energetic neutral atom map is being misinterpreted, or the Voyager 1 magnetic field measurement is being misinterpreted, or the theoretical framework connecting these two observations to the underlying physical system is missing something important. Most scientists who have studied this carefully believe the third option is most likely. The theoretical framework is missing something. Probably something about the way the interstellar magnetic field drapes and wraps around the heliosphere. Is something about the behavior of the boundary layer where the two regimes of physics, solar wind physics and interstellar medium physics, overlap and interact. The models treat these two regimes as relatively cleanly separable, with a well-defined boundary between them. The data suggests the reality is more complex, more interpenetrating, more mutually influential than the clean theoretical picture allows. And so, we arrive at the question that has been building since the beginning of this story. The question that the plasma density anomaly and the magnetic field discrepancy and the electromagnetic hum and the twisted heliotail are all circling around, each from a different direction. What does the heliosphere actually look like? Not what it looks like in the textbook diagrams, the smooth teardrop shape with neatly labeled boundary regions. What does it actually look like in 3 dimensions, in its full physical reality, as a dynamic structure moving through a turbulent medium and responding to a constantly varying solar wind? The honest answer is that we do not know. And the reason we do not know, despite having 2 spacecraft in the interstellar medium and decades of remote sensing data, is that we have never been able to see the heliosphere from the outside. We are inside it. We are sampling it from within at 1 or 2 points at one moment in its dynamic evolution. We have no external vantage point from which to observe its true shape the way you might photograph a balloon from across the room. The energetic neutral atom technique used by the interstellar boundary explorer was the closest thing to an external view we have ever had. Energetic neutral atoms are created at the boundary region when fast-moving charged particles exchange charge with slow-moving neutral atoms, becoming neutral themselves and therefore no longer confined by magnetic fields. They fly away from the boundary in straight lines, and when they arrive at the spacecraft in the inner solar system, their direction of arrival tells you something about where they came from, and their energy tells you something about the conditions at their point of origin. By mapping the arrival directions of these atoms, the interstellar boundary explorer built up a picture of the boundary region as seen from the inside, like taking a long exposure photograph of a building by standing inside and mapping where light comes through the walls. That picture showed the unexpected structure of the heliotail. It also showed, in the nose region, something interesting about the termination shock and heliosheath that became more puzzling when compared against Voyager 1's in situ measurements. The remote sensing picture and the direct in situ measurements did not fully agree on the thickness of the heliosheath. The energetic neutral atom map implied a heliosheath somewhat thinner than what Voyager 1's travel time through the region suggested. though the discrepancy was within the range of theoretical uncertainty about how the heliosheath's thickness varies with direction and over time. The point is not that any single measurement is wrong. The point is that the system is more complex than the models assumed, and the complexity is showing up simultaneously in multiple independent data sets. The heliosphere is not the textbook teardrop. It is something more irregular, more dynamic, more sensitive to local variations in the interstellar environment than any pre-Voyager model fully captured. There is a concept in theoretical physics and fluid dynamics called magnetic reconnection. It is a process by which magnetic field lines from two different regions that are in contact with each other, field lines pointing in different directions, can break and reconnect in a new configuration, releasing stored magnetic energy in the process. Magnetic reconnection is a fundamental process in solar physics. It drives solar flares and coronal mass ejections. It operates in the magnetospheres of planets. It plays a role in the dynamics of stellar coronae. It is a well-studied process in laboratory plasma physics. There is significant theoretical reason to believe that magnetic reconnection also operates at the heliopause, specifically at the points where the solar wind's magnetic field and the interstellar magnetic field come into direct contact. If the solar field and the interstellar field are pointing in different enough directions, at those contact points, reconnection can occur. When it does, it creates a channel through which interstellar material can flow into the heliosphere, and through which solar wind material can escape into the interstellar medium. It locally modifies the magnetic field configuration on both sides of the boundary, and it can create the kind of blurring and ambiguity at the boundary edge that Voyager 1 detected in the years after its heliopause crossing. Those brief excursions back into heliospheric conditions that suggested the boundary was not as clean as expected. Magnetic reconnection at the heliopause is not a fringe idea. It appears in peer-reviewed theoretical papers going back decades. But whether it is actually occurring, at what rate, over what area of the heliopause surface, and with what consequences for the structure of the near heliospheric interstellar medium, is not something that has been directly confirmed by any measurement. Voyager 1 is measuring the integrated result of whatever processes are operating at the heliopause. It cannot tell us directly whether reconnection is responsible for the boundary's complexity. What it can tell us is that the complexity is real. That the boundary region is not simply a passive interface where one medium ends and another begins, but an active zone where processes are occurring that we have not fully characterized and that may be exchanging material, energy, and magnetic field between the solar system and the interstellar medium in ways that have ongoing consequences for both. Now, I want to introduce a thread that has been running quietly beneath everything we have discussed so far, a thread that connects the plasma density anomaly, the electromagnetic hum, the magnetic field discrepancy, and the heliotail asymmetry into a single coherent puzzle. The thread is about scale. Every anomaly Voyager 1 has revealed at the boundary of the heliosphere involves a mismatch between the scale at which we can model the physics and the scale at which the physics actually operates. The theoretical models of the heliosphere are global models. They describe the large-scale structure of the heliosphere using bulk averages of solar wind properties and interstellar medium properties. They treat the solar wind as a fluid with average velocity, average density, average magnetic field. They treat the interstellar medium as a medium with average density, average temperature, average field direction. These bulk averages are the only practical way to build a tractable model of a system that spans hundreds of astronomical units in 3 dimensions. But the solar wind is not actually a smooth fluid. It is a turbulent, structured flow with variations on scales from thousands of kilometers to tens of astronomical units. Coronal mass ejections create enormous transient pressure pulses. Fast and slow wind streams interact with each other, and creating compressed regions and rarefaction regions that propagate outward for vast distances. The solar activity cycle modulates the overall energy output of the solar wind on an 11-year period. All of this structure is real and physically important, but incorporating it fully into a global heliospheric model is computationally prohibitive. Similarly, the interstellar medium is not a smooth fluid with uniform properties. It has filaments, sheets, cloudlets, density fluctuations on scales from astronomical units to light years. The magnetic field has a tangled, turbulent component superimposed on its large-scale average direction. The cosmic ray population has energy-dependent anisotropies and time variations driven by distant events. Again, real and physically important, this but too complex to be fully incorporated into a tractable global model. The heliosphere exists at the interface between these two complex, structured, turbulent media. Its boundary is shaped by the detailed, fluctuating properties of both, and the models that predicted what Voyager 1 would find at that boundary were built using average, smooth approximations of both media. When Voyager 1 got there and measured the actual, detailed, specific properties of the actual, detailed, specific piece of interstellar medium surrounding our solar system at this particular moment in its journey, it found that the real values differed from the averaged predictions. This should perhaps not have been surprising, but the magnitude of some of the differences, particularly the plasma density being off by a factor of 3 to 4, suggests that the specific local environment the solar system is currently embedded in differs from what the models assumed by more than the expected range of random variation. We may be in an unusually dense pocket of the local interstellar cloud, or the local interstellar cloud itself may have more internal structure than was previously recognized. Or there may be a physical process at the heliopause, such as charge exchange or magnetic reconnection, that is locally enhancing the plasma density just outside the boundary in a way that is not properly accounted for in the models. What is clear is that the single most direct measurement of the density of the local interstellar medium, made by the only spacecraft ever to have been there, disagrees with the theoretical prediction by a factor large enough to matter. And the consequences of that disagreement extend far beyond heliospheric physics. Because the density of the interstellar medium affects the rate at which stars can form from collapsing gas clouds. It affects the propagation of supernova shock waves through the galaxy. It affects the chemistry of the interstellar medium, since denser regions support different molecular reactions. It affects the flux of cosmic rays reaching planetary surfaces. It affects the rate at which comets in the outer reaches of stellar systems are perturbed by passing interstellar clouds and sent inward toward their host stars. The density of the interstellar medium is not a parochial quantity of interest only to heliospheric physicists. It is a fundamental input to models of galactic dynamics, stellar evolution, and astrochemistry. And we now have reason to believe that our best estimates of the local value of that fundamental quantity may be off by a factor of 3 to 4. Imagine you are an engineer designing a bridge. You need to know the density of the steel you are using. You have a theoretical estimate of that density based on the steel's composition. You build the bridge. Years later, someone directly measures the density of the actual steel in the bridge and finds it is 3 to 4 times higher than your estimate. The bridge may still be standing. The basic physics of bridge design is still valid. But every calculation you made using that density estimate needs to be revisited. Every safety margin needs to be recalculated. Every design decision that depended on that number needs to be re-examined. That is the situation in heliospheric physics and, to some extent, in interstellar medium physics more broadly. The basic equations are still valid. The foundational framework is still intact. But the specific numbers that go into those equations, the boundary conditions, the local values of key physical quantities need to be revisited. And until we have more direct measurements from different points in the local interstellar medium taken by spacecraft that do not yet exist, the uncertainty will remain. There is one more finding from Voyager 1 that I have been holding back, not because it is less important than the others, but because it requires everything we have discussed so far to be fully appreciated. It involves not the interstellar medium, not the magnetic field, not the plasma density, but the cosmic rays themselves, and specifically a pattern in the cosmic ray data that emerged in the first years after the heliopause crossing, and that has continued to deepen in subsequent years. When Voyager 1 crossed the heliopause in 2012, the galactic cosmic ray flux jumped sharply, as expected. But what happened after that jump is not what any model predicted. The cosmic ray flux did not simply level off at a constant interstellar background value. Instead, it continued to rise slowly but measurably for years after the crossing. It was still rising as of the most recent published analyses. The spacecraft is now more than 40 astronomical units beyond the heliopause, deeper into the interstellar medium than any previous model considered in detail, and the cosmic ray flux is still increasing. This means one of two things. Either the region immediately outside the heliopause is still shielding some cosmic rays, perhaps through the draping of the heliospheric magnetic field that extends some distance beyond the heliopause itself, and that shielding is diminishing as Voyager 1 moves farther away. Or the local interstellar medium has a gradient in cosmic ray density, with the region immediately outside the heliosphere having fewer cosmic rays than the deeper interstellar medium, for reasons that are not related to the heliosphere's direct influence. If the first explanation is correct, it means the heliosphere's magnetic influence extends significantly farther into the interstellar medium than models predicted, creating what amounts to an extended magnetic halo around the heliosphere that provides some level of cosmic ray deflection even beyond the formal boundary of the heliopause. If the second explanation is correct, it means the local interstellar medium has a cosmic ray gradient, a variation in cosmic ray density with position that is not predicted by standard models of cosmic ray propagation in the interstellar medium. Such a gradient would require a source or sink of cosmic rays in the local neighborhood, something accelerating or removing cosmic rays at a rate sufficient to create the observed density variation over the scale of tens to hundreds of astronomical units. Neither explanation is without problems, and the possibility that both effects are operating simultaneously, each contributing to part of the observed trend, cannot be ruled out. What is clear from the data is that the simple picture of a heliosphere surrounded by a uniform, isotropic cosmic ray background is wrong. The reality is more structured, more spatially variable, and more dynamically complex than the simple picture allowed. The rising cosmic ray flux has a direct, tangible significance for the question of life in the solar system, because cosmic rays are mutagenic. They damage DNA. They ionize the upper atmosphere, driving chemical reactions that affect the ozone layer. They can, at high enough intensities, increase the rate of genetic mutation and increase the risk of radiation-related cellular damage. The heliosphere provides partial protection against galactic cosmic rays. The level of that protection depends on the cosmic ray flux just outside the heliopause and on the detailed structure of the heliosphere's magnetic shielding. If the cosmic ray flux just outside the heliopause is higher than models predicted, and if the heliosphere's shielding efficiency is different from what models predicted, then the actual level of cosmic ray bombardment reaching the inner solar system may also differ from model predictions. Not drastically. Not in a way that would threaten life on Earth in the current configuration, but in a way that matters for precise calculations of long-term biological and atmospheric effects, and in a way that would matter much more if the heliosphere were ever significantly compressed by a denser interstellar medium. Which brings us back to the question of the solar system's trajectory through the galaxy, and to the fact that we are near the edge of the local interstellar cloud. Because if the solar system is approaching a denser region of the interstellar medium, the heliosphere will eventually be compressed, the heliopause will move inward, and the cosmic ray shielding of the inner solar system will decrease. By how much and over what time scale depends entirely on the properties of the medium we are moving into. Properties that Voyager 1's measurements have shown us we cannot reliably predict from theory alone. When you step back from the individual anomalies, when you look at all of it together, the plasma density discrepancy, the magnetic field orientation mismatch, the electromagnetic hum, the twisted heliotail, the extended cosmic ray gradient, the complex and dynamic heliopause boundary, what you see is not a collection of unrelated puzzles. You see a single underlying reality asserting itself against the smooth, simplified picture that theoretical models had constructed. The underlying reality is this: the heliosphere exists in a specific, particular, locally variable, dynamically evolving piece of the galaxy. It is not surrounded by a featureless, uniform, interstellar medium. It is embedded in a cloud with internal structure, traveling toward a boundary whose properties we cannot yet directly measure, wrapped in a magnetic field whose true direction we cannot definitively determine, surrounded by a plasma whose density and oscillation properties differ from our best predictions. The heliosphere responds to all of this in real time, constantly adjusting its shape and boundary structure to maintain the pressure balance that defines it. And those adjustments, those responses, those dynamic processes at the boundary are things our models captured only in their broadest outline. Voyager 1 has given us the detailed picture, and the detailed picture is surprising. But here is what I find most remarkable about all of this, and what I want you to hold in your mind as we move into the final part of this story. Every single one of the anomalies Voyager 1 has revealed was discovered by scientists who did not go looking for it. The plasma density anomaly was found by researchers analyzing the plasma wave data after a solar eruption caused a detectable disturbance in the interstellar medium, giving them a way to convert the wave frequency into a density measurement. The electromagnetic hum was noticed as a faint, persistent signal between the louder transient events by a team that was specifically looking at the quiet time data to understand the background conditions. The cosmic ray gradient was identified by comparing the particle flux data across multiple years of measurements and recognizing that what should have been a flat line was instead a slowly rising slope. None of these were discoveries made by instruments designed specifically to find them. They were made by scientists paying close attention to data from instruments designed decades ago for different primary purposes, extracting new science from old hardware by the simple and irreplaceable act of looking carefully at what the numbers actually say, rather than what the models said they should say. This is how the most important discoveries in the history of science have always worked, not primarily through grand planned expeditions to find known things, but through the careful, attentive examination of unexpected patterns in data that was collected for other reasons. Penicillin, the cosmic microwave background, pulsars, the accelerating expansion of the universe. In every case, the discovery was made by someone who was paying attention to something that the prevailing model said should not be there. Voyager 1 is 47 years old. Its designers are in their 80s. Its programming language is extinct. Its data transmission rate is slower than the internet connections of the early 1990s. And it is still, right now, in this moment, returning data that is changing how we understand the structure of the solar system, the properties of the local interstellar medium, and the boundary between the domain of our Sun and the larger galaxy it inhabits. That fact alone deserves a moment of quiet contemplation before we go further. Because what comes next in this story, what Voyager 1's data implies about the deeper structure of the boundary region, and about a possibility that has only recently become a subject of serious scientific discussion, is the part that will stay with you. There is a question that heliospheric physicists have been circling for the better part of a decade, one that the accumulation of anomalies from Voyager 1 has made increasingly difficult to avoid. It is not a question about any single measurement or any single instrument. It is a question about the overall architecture of our theoretical understanding, about whether the framework itself, the conceptual structure within which all the individual measurements are interpreted, is missing a fundamental element. The question is this: is the heliosphere a closed system or an open one? On the surface, this sounds like a technical question for specialists, but its implications reach far beyond the details of plasma physics and boundary layer dynamics. Because if the heliosphere is more open than we thought, if material, energy, and magnetic field are exchanging more freely between the solar system and the interstellar medium than any current model allows, then the solar system is not the isolated, self-contained bubble we have imagined it to be. It is something more like a permeable membrane, a region where solar and interstellar physics interpenetrate in ways that have ongoing consequences for the chemistry of the outer solar system, for the distribution of cometary material in the distant reaches beyond Neptune, for the long-term evolution of the planets themselves, and perhaps for questions about habitability that extend far beyond our own solar system, to every stellar system embedded in a similar interstellar environment. Before Voyager 1 crossed the heliopause, the prevailing theoretical picture treated the heliosphere as essentially closed. The heliopause was a boundary that solar wind material could not cross in significant quantities because the pressure balance at the boundary kept solar and interstellar material on their respective sides. Some interstellar neutral atoms could penetrate the heliosphere because, being electrically neutral, they are not deflected by magnetic fields, and they do penetrate, traveling deep into the inner solar system where they can be detected. But charged particles, the bulk of the solar wind on one side and the bulk of the interstellar plasma on the other, were supposed to stay separated. Magnetic reconnection, as I described earlier, provides a mechanism for breaching this separation. But in the pre-Voyager era of heliospheric modeling, reconnection at the heliopause was generally treated as a secondary effect. Important perhaps in local regions of the boundary, but not significant enough to fundamentally alter the closed system picture. What the data from Voyager 1 has done collectively and cumulatively is to make the secondary effect assumption much harder to defend. Consider the brief excursions back into heliospheric conditions that Voyager 1 detected in the first years after its heliopause crossing. If those excursions represent folds in the heliopause that the spacecraft was passing through, they suggest a heliopause that is geometrically complex and dynamic, not the relatively smooth interface that closed system models assumed. A folded, rippled heliopause has a much larger surface area than a smooth one. Larger surface area means more boundary contact between solar and interstellar material. More boundary contact means more opportunity for reconnection and for mixing across the boundary. The geometry itself, if it is as complex as the excursion data suggests, makes the open system possibility more physically plausible. Now, add the electromagnetic hum. If the local interstellar medium just outside the heliopause has a persistent background level of plasma wave activity, driven partly by the heliosphere's own dynamics propagating outward, then the heliosphere is not just passively sitting in the interstellar medium. It is actively modifying the medium around it. The heliosphere is leaving an electromagnetic footprint in the interstellar plasma, maintaining a zone of elevated wave activity around itself that extends beyond the formal boundary. This zone is not predicted by closed system models. It requires that energy from inside the heliosphere is leaking outward in a form that persists in the external medium. Now add the extended cosmic ray gradient. If cosmic rays are still being influenced by the heliosphere's magnetic field beyond the heliopause, then the heliosphere's magnetic reach extends farther than its formal boundary. The magnetic field lines of the solar wind, which are rooted in the sun and spiral outward, do not simply terminate at the heliopause. They drape into and around the boundary region. Some of them may connect directly to interstellar field lines through reconnection events, creating temporary magnetic connections that thread across the formal boundary and allow particles to move between the two regions. In a system where magnetic field lines connect the inside to the outside, the closed system picture is simply wrong as a description of particle transport, and now add the plasma density anomaly. If the electron density of the interstellar medium just outside the heliopause is 3 to 4 times higher than models predict, one possible explanation, and it is not the only one, but it is a physically motivated one, is that the boundary region is accumulating material. That charge exchange processes at the heliopause, where fast solar wind protons grab electrons from slow interstellar neutrals and become neutral themselves, are creating a local enrichment of plasma in the near heliopause interstellar medium. This process is known to operate. It is included in some models. But if the rate of charge exchange is higher than assumed, perhaps because the surface area of the heliopause is larger than assumed due to its folded geometry, perhaps because the local density of interstellar neutrals is higher than assumed, then the resulting plasma enrichment could be substantial. In this picture, The elevated plasma density just outside the heliopause is not a property of the undisturbed local interstellar medium. It is a property of the heliosphere's interaction zone, a local modification of the interstellar medium created by the heliosphere's own processes. And if that is correct, then Voyager 1's density measurement, rather than telling us about the ambient interstellar medium, is telling us about a modified boundary layer, whose properties are determined by the heliosphere itself. If this interpretation is correct, it has a fascinating implication. It means that Voyager 1 has not yet fully escaped the heliosphere's influence, even 40 astronomical units beyond its formal boundary. It means the heliosphere projects its influence into the surrounding medium through electromagnetic, chemical, and particle transport processes that create an extended interaction zone larger than any current model predicts. And it means that to sample the truly undisturbed local interstellar medium, a future spacecraft would need to travel considerably farther than anyone had previously assumed. How far? Nobody knows. But estimates based on the scale of the various phenomena Voyager 1 has detected suggest the transition from heliosphere-influenced medium to genuinely unperturbed interstellar medium might not be complete until somewhere between 200 and perhaps 300 astronomical units from the Sun. At Voyager, 1's current speed of approximately 17 kilometers per second, traveling from the current position of 160 astronomical units to 300 astronomical units would take roughly 45 to 50 additional years. Voyager 1 will be long silent before it gets there. This is a hard thing to sit with. The only spacecraft we have ever placed in the interstellar medium will run out of power before it reaches the region where the interstellar medium is truly undisturbed. We will get partial data. Significant, evaluable, irreplaceable data, but partial. The full picture of the heliosphere's extended influence zone will not be directly measured by any instrument currently in existence or currently planned. There is a mission concept, studied for years at the Jet Propulsion Laboratory and various academic institutions, called the Interstellar Probe. Its goal would be to send a purpose-built spacecraft to a distance of at least 1,000 astronomical units from the Sun, fast enough to get there within the professional lifetime of the scientists who design it, perhaps 50 years, using a combination of advanced propulsion and a close solar flyby to achieve speeds of perhaps 20 to 30 kilometers per second. At that distance, 1,000 astronomical units, the spacecraft would be genuinely deep in the local interstellar medium, far beyond any plausible influence of the heliosphere. Its measurements would, for the first time, give us a direct sample of the undisturbed local interstellar environment. The Interstellar Probe is not funded. It is not in development. It exists in the category of missions that scientists dream about and write white papers advocating for. Missions whose scientific value is recognized and celebrated, but whose cost and complexity make them perpetually deferred in favor of more immediate scientific priorities. Every decade, when the scientific community goes through its formal priority-setting process, the interstellar probe concept is discussed, praised, and then set aside. That may change. Because the data from Voyager 1 has fundamentally altered the scientific context in which such a mission would be evaluated. Before Voyager 1's crossing, the local interstellar medium was thought to be broadly predictable from theory. A dedicated interstellar probe would be scientifically valuable, yes, but it would be exploring a region whose properties were approximately known. After Voyager 1, the local interstellar medium has revealed itself as a place full of surprises. with properties that differ from predictions in multiple ways simultaneously, and whose detailed characterization requires measurements from a purpose-built platform capable of making comprehensive observations at a range of distances. The scientific case for an interstellar probe has never been stronger. But let us pull back from mission planning and return to the data, because there is one more thread in this story that has not yet been fully explored. A thread that connects everything Voyager 1 has told us about the heliosphere's boundary to a question about the history of life on Earth. The question is about what happens to the heliosphere when the solar system passes through a denser region of the interstellar medium. And the answer, worked out theoretically over the past several decades, is remarkable. When the solar system encounters a significantly denser region of the interstellar medium, the increased pressure compresses the heliosphere. The termination shock moves inward, the heliopause moves inward. In an extreme case, the heliopause could be compressed to a distance comparable to the orbit of Saturn or even Jupiter. In such a scenario, the outer planets would be exposed to the full flux of galactic cosmic rays and the full density of interstellar gas, with no heliospheric protection. The inner planets, including Earth, would be exposed to a cosmic ray flux orders of magnitude higher than they experience today. How likely is this? And has it happened before? The solar system has been traversing the interstellar medium for 4.6 billion years. During that time, it has passed through many different regions of the galaxy. It has spent time in the spiral arms of the Milky Way, where the interstellar medium is denser and more structured. It has passed through or near star-forming regions, molecular clouds, and the remnants of supernova explosions. The local bubble itself, the enormous hot cavity our solar system currently inhabits, was carved by perhaps 15 to 20 supernova explosions over the past 10 million to 20 million years. At least some of those explosions occurred close enough to the solar system to have had direct effects. Several years ago, a group of scientists examining deep-sea sediments found elevated concentrations of a specific isotope, iron-60, at sediment layers corresponding to an age of roughly 2.2 million years ago, and again at around 6.5 million years ago. Iron-60 is a radioactive isotope with a half-life of about 2.6 million years. It is not produced by normal stellar nucleosynthesis in significant quantities and is not naturally abundant on Earth. Its most plausible source is the ejecta of a nearby supernova explosion, material that was blown into the local interstellar medium and eventually incorporated into the dust that settled through Earth's atmosphere onto the ocean floor. So the presence of iron-60 in Earth's sediments at these ages is direct evidence that one or more supernovae exploded close enough to the solar system to deliver their ejecta to Earth within the past few million years. The closest estimate for the distance of the explosion responsible for the 2.2 million year signal is somewhere between about 100 and 300 light years. That is close on the scale of the galaxy, close enough that the supernova remnant, expanding outward as a shell of hot gas and energetic particles, would have swept past the solar system, temporarily increasing the local density and energetics of the interstellar medium. When a supernova remnant sweeps past the heliosphere, two things happen. First, the pressure of the expanding hot gas compresses the heliosphere inward. Second, the remnant carries with it an enhanced flux of energetic particles, cosmic ray accelerated at the shock front of the expanding remnant. Both of these effects, the heliosphere compression and the enhanced cosmic ray flux, would result in a temporary but potentially significant increase in the cosmic ray bombardment reaching the inner solar system. The timing of the Iron 60 signal at 2.2 million years ago corresponds intriguingly to a period that has been independently associated with elevated rates of genetic mutation and biological change in the fossil record. The emergence of the genus Homo, the lineage that eventually led to modern humans, dates to approximately 2.8 million years ago. The period around 2 to 3 million years ago was one of marked climatic variability and biological turnover in Africa, where the earliest members of the human lineage were evolving. The connection between a nearby supernova, potential heliosphere compression, elevated cosmic ray flux, increased mutation rates, and the emergence of the human lineage is speculative. It is explicitly speculative. The causal chain involves too many uncertain steps to be stated as established science. But it is not crazy. And the reason it is not crazy is precisely because of what Voyager 1 has revealed about how sensitive the heliosphere actually is to the properties of the surrounding interstellar medium, how the boundary is more dynamic, more permeable, and more responsive to external conditions than the clean, theoretical picture suggested. If the heliosphere compresses significantly in response to modest increases in interstellar pressure, it increases well within the range of variation expected as the solar system moves through different regions of the local bubble, then the cosmic ray flux reaching Earth is not a constant background. It is a variable that has fluctuated throughout the history of life on this planet, sometimes significantly, driven by the solar system's trajectory through the galaxy. We are, in a very real sense, biological products of a journey through the galaxy. The environments the solar system has passed through, the clouds it has entered and exited, the supernovae that have exploded in its neighborhood, the compressed and expanded heliospheres that resulted, all of these have shaped the radiation environment of Earth throughout the history of life. Evolution has occurred not in a static cosmic environment, but in a fluctuating one, that driven partly by forces originating billions of kilometers beyond the orbit of Neptune. Voyager 1 did not discover this connection directly. That would be too much to ask of one spacecraft at one location at one moment in time. But what Voyager 1 has done is make this connection scientifically serious in a new way, by demonstrating that the heliosphere's boundary is more complex, more dynamic, and more sensitive to the interstellar environment than models predicted. It has strengthened the scientific basis for taking seriously the idea that the cosmic environment beyond the heliosphere has had and continues to have a non-trivial influence on the conditions for life in the inner solar system. That is not a small thing. Now, I want to come back to something I mentioned much earlier in this story, a number that I asked you to hold in your mind, the plasma electron density measured by Voyager 1 in the local interstellar medium, derived from the plasma oscillation events caused by solar eruptions propagating through the boundary region. The value was approximately 0.13 electrons per cubic centimeter, 3 to 4 times higher than the pre-crossing theoretical predictions. I asked you to hold that number because it was going to matter later. And now we are at the point where it matters in a different way than you might have anticipated. That density measurement was not just important for heliospheric physics, it was important because it gave scientists the first direct, in situ measurement of the electron density of the local interstellar medium, and a quantity that astronomers have been trying to measure accurately for decades using a variety of indirect techniques. Radio observations of distant pulsars, for example, are used to infer the average electron density of the interstellar medium along the line of sight by measuring the frequency-dependent dispersion of pulsar radio pulses. The local contribution to that dispersion measure, the contribution from the immediate solar neighborhood, has always been uncertain because it was derived from models rather than direct measurement. Voyager 1's measurement puts a direct observational anchor on that local contribution. And the fact that the measured value is significantly higher than theoretical predictions means that some of the dispersion measure-based distances to nearby pulsars and other radio sources may need to be revised. The distances were calculated assuming a certain local electron density. If the actual local density is higher, the distances need to be adjusted, not by enormous amounts, not by factors of 3 to 4 in the distances themselves, but by amounts that matter for precision astrometry and for the detailed study of nearby pulsars, fast radio bursts, and other phenomena whose analysis depends on an accurate model of the local interstellar electron density. This is the cascading nature of a precise direct measurement in astrophysics. It does not just answer the question it was designed to answer. It provides a calibration anchor for a whole range of other measurements and analyses that were previously subject to the same theoretical uncertainty it resolves. And here is something that I find genuinely wonderful about this. There's something that exemplifies the way science accumulates meaning through the intersection of unrelated inquiries. The plasma wave instrument aboard Voyager 1 was not designed to measure the electron density of the local interstellar medium. It was designed to study plasma waves in planetary magnetospheres, in the magnetospheres of Jupiter and Saturn specifically, decades ago, when the spacecraft was still in the inner solar system. The fact that it can be used to derive an interstellar electron density measurement is a consequence of the basic physics of plasma oscillations, physics that the instrument's designers understood perfectly well, but whose application to interstellar medium science was not the purpose for which the instrument was built. The instrument has, in a sense, lived multiple scientific lives, born as a planetary magnetosphere probe, repurposed as a heliospheric boundary detector, and now functioning as an interstellar medium spectrometer. None of these roles was exclusively planned. Each grew from the previous one as the spacecraft moved and the scientists kept paying attention. There is a lesson in this that goes beyond the specific science. The most valuable thing we can do with any instrument, any spacecraft, any data set is to keep asking what else it can tell us beyond what it was designed to tell us. The universe almost always has more information in any given set of measurements than was put there intentionally. The act of scientific discovery is largely the act of finding that information. Voyager 1 has been delivering that extra information for 47 years, and in its final years of scientific operation, with its instruments failing one by one as the power declines, it is delivering data that is more surprising and more scientifically consequential than anything returned during its celebrated planetary encounters in the late 1970s. The flybys of Jupiter and Saturn were the mission's designed purpose, and they were magnificent. But this, the slow, patient accumulation of impossible measurements from beyond the edge of the solar system, this is what Voyager 1 will ultimately be remembered for. Because what it has found is not just a set of anomalies in heliospheric physics. What it has found is evidence that the boundary between our solar system and the galaxy is not the clean, well-understood interface that 4 decades of theoretical work had produced. It is instead a complex, dynamic, partially open boundary whose behavior involves processes we have not fully characterized in an environment whose properties differ from our best predictions, within a cosmic neighborhood whose history of violence and change has left physical evidence in the deep sediments of Earth's ocean floors. We did not know the full shape of the ocean we are swimming in. Voyager 1 is one of the first instruments ever to touch the water beyond it, and the water is different from what we expected. Which brings us to the final question, not a question about plasma physics or boundary conditions or electron density or magnetic field orientation, a deeper question. The question that all of this data, accumulated over 47 years from a spacecraft that should, by all rights, have failed decades ago, ultimately forces us to confront. What are we actually part of? We think of the solar system as our home. We think of the sun as our star, the planets as our neighbors, the heliosphere as the walls of our cosmic house. But the heliosphere is not a wall. It is not a sealed container. It is a negotiation constantly renegotiated between the energy output of the sun and the pressure of a galaxy that has its own history, its own violence, its own magnetic structure, its own particle populations, none of which was created for us, and none of which is indifferent to us. The heliosphere compresses and expands on timescales of thousands to millions of years as the solar system moves through different regions of the interstellar medium. The cosmic ray flux reaching Earth has varied accordingly. The chemistry of the upper atmosphere has responded. The mutation rates in living organisms have fluctuated. The history of life on this planet is not just a story about geology and biology, it is a story about the solar system's trajectory through the galaxy and about the fluctuating shelter provided by a magnetic bubble whose properties are only now, with Voyager 1's data, beginning to be directly understood. We are not isolated from the galaxy. We are embedded in it, protected from the worst of it by a bubble of magnetized plasma that the sun creates and that the galaxy continuously tries to compress. That protection is real and substantial, but it is not absolute, and it is not permanent. The solar system will continue to move. The interstellar environment will continue to change. The heliosphere will continue to respond. And somewhere in that ongoing negotiation, the conditions for life in the inner solar system will be continuously, subtly shaped. 47 years ago, a group of engineers and scientists at the Jet Propulsion Laboratory launched a spacecraft roughly the size of a small car into a trajectory calculated with pencils and slide rules and the earliest digital computers. They attached to it instruments designed to study worlds none of them had ever seen up close. They gave it a golden record containing the sounds of a planet that wanted, however naively and beautifully, to say hello to anyone who might ever find it. And they pointed it outward. They did not know it would still be transmitting after 47 years. Some of them privately doubted it would survive the journey through the asteroid belt. They did not know it would cross the termination shock, traverse the heliosheath, and become the first human object to enter interstellar space. They did not know it would find a plasma density 3 to 4 times higher than any model predicted, or detect an electromagnetic hum with no satisfying explanation, or reveal a heliopause more complex and dynamic than anyone had imagined, or provide the first direct calibration anchor for the local interstellar electron density, or raise serious questions about the open or closed nature of the heliosphere's boundary. They knew none of this. They just built it as well as they could, launched it, and kept listening. And here is the thing that I keep returning to, the thought that I find impossible to fully process, and equally impossible to stop thinking about. The signals that Voyager 1 is sending right now, in this moment, carrying data about the plasma conditions of the local interstellar medium, are traveling at the speed of light and will arrive at the Deep Space Network antennas in roughly 22 hours. The engineers who receive those signals will convert them into measurements, quality check them, archive them, and make them available to scientists around the world. Those scientists will analyze the measurements, compare them against models, write papers, argue about interpretations, and gradually, through a process that is contentious and self-correcting and deeply human, arrive at something closer to the truth about what Voyager 1 is experiencing in the space between the stars. This process, the sending and receiving and analyzing and arguing, is itself one of the most extraordinary things happening on this planet right now. It is a conversation, extended over 22-hour signal delays between human minds in buildings in California and a machine drifting in the cold between the stars, a machine that carries a fading warmth from the decay of a radioactive metal, that turns that warmth into electricity, that turns that electricity into a whisper of radio waves aimed back at a pale blue dot from a distance that makes the dot effectively invisible to any instrument on the spacecraft itself. Voyager 1 cannot see us. It has no camera pointed at Earth. Even if it did, the Sun at Voyager 1's distance would be an unremarkable point of light, one bright star among many, lost in the sweep of the Milky Way. The spacecraft has no way to know whether the messages it sends are being received, no way to know whether the civilization that built it still exists, no way to know whether the buildings where its signals arrive are staffed by people who still understand the data formats it uses, and yet it keeps transmitting. Because that is what it was built to do. Because the instructions encoded in its memory 47 years ago told it to keep transmitting, and the instructions have not been countermanded, and the power has not yet run out. And so the whisper continues. At some point in the next decade, depending on exactly how the power declines and which instruments fail in what order, the last scientific instrument aboard Voyager 1 will cease to function. The spacecraft will go silent in the scientific sense. It may continue to transmit a carrier signal for some years after that, a heartbeat without information, just a tone confirming it is still out there. And then the carrier will drop below the threshold of detectability, and Voyager 1 will become simply a piece of metal moving through the interstellar medium at 17 kilometers per second, carrying its golden record into a silence that will last until the universe itself changes beyond recognition. Long after the Sun has expanded into a red giant and swallowed the Earth and cooled into a white dwarf, Voyager 1 will still be moving, still carrying the golden record, still carrying the memories of the civilization that built it, encoded in the grooves of a disk that will survive in the near-zero temperature of the interstellar medium for billions of years, perhaps longer. Perhaps essentially forever relative to any time scale that has meaning for us. The spacecraft will never reach another star system. The distances are too vast. But it will drift through the interstellar medium of the Milky Way, perhaps eventually into another galaxy, as the local group of galaxies continues its slow gravitational collapse, for a duration that makes the entire history of life on Earth seem like the briefest of moments. We sent it. We built it with our hands and our minds and the physics that nature allowed us to discover. And in the act of building it and launching it and keeping it alive for 47 years through dedication and ingenuity and the refusal to stop listening, we have learned that the boundary between our home and the galaxy is more complex, more surprising, and more consequential than we knew. We have learned that the universe does not respect the clean lines we draw in our models, that reality has structure and variation and surprise at every scale. And down to the individual electron densities and plasma wave frequencies of the specific cubic centimeter of interstellar space that our specific spacecraft happens to be traversing at this specific moment in the solar system's 4 billion-year journey through the galaxy. We have learned that the heliosphere is not a wall. It is a conversation, a continuous, dynamic, imperfect negotiation between the sun's energy and the galaxy's pressure, between the inside and the outside, between the familiar and the unknown. And we are still listening to what that conversation is saying. Voyager 1 crossed into something. Scientists have no complete explanation for what it found there. The data does not fit the models. The boundary is not what we thought. The medium beyond it is not what we predicted. The hum in the plasma has no confirmed source. The density is wrong by a factor of 3 to 4. The magnetic field points in a direction that two independent measurement methods cannot fully reconcile. The cosmic ray gradient extends farther than any model allows. These are not failures, they are invitations. Each one is the universe pointing at a gap in our understanding and saying quietly and without drama that there is more here than you have seen yet. Keep looking. The spacecraft that issued that invitation is 47 years old. It weighs 722 kilograms. It runs on 40 watts of power. It is approximately 23.8 billion kilometers from the Sun. It is the farthest human-made object in the history of civilization. And it still has things to tell us.